Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to describe the PLU decomposition. So in this topic, we will review row operations as represented by matrices and the algorithm of Gaussian elimination with partial pivoting. We will work through an example of performing Gaussian elimination with partial pivoting, but we will be using the row operation matrices. Based on this example, we will observe that we should be able to write any matrix as the product of three matrices P, L, and U, where P is a permutation matrix, L is a lower triangular matrix, and U is an upper triangular matrix in row echelon form. We will see that if we find these three matrices, then we can significantly speed up solving systems of linear equations when the target vector continues to change, but where the matrix itself remains constant. Finally, we will describe an algorithm for finding P transpose, L, and U, and work through an example. Now, to begin, this algorithm is normally called the LU decomposition. However, in this course, I will be describing this as the PLU decomposition, as after all, the matrix will be being decomposed into three separate matrices. The P matrix is going to be a permutation matrix. Now, the PLU decomposition says that every M by N matrix A can be written as the product of three matrices P, L, and U, where P is an M by M permutation matrix, L is a lower triangular M by M matrix with all ones on the diagonal, and U is an upper triangular M by N matrix. Now, to build this, we will actually use a constructive proof. What we will do is we will begin with an arbitrary matrix and then demonstrate that from this arbitrary matrix we can determine these three matrices P, L, and U. Now we are going to be using Gaussian elimination with partial pivoting to find these three matrices. The partial pivoting, that is the component where we swap rows, will be that aspect of Gaussian elimination that produces the permutation matrix. If you happen to ignore partial pivoting, then the P matrix will likely end up being the identity matrix, but the result or the usefulness will be something that is less accurate. Now recall that with Gaussian elimination, the goal was to find a row equivalent matrix that is in row echelon form. That is, we proceeded by finding a sequence of row operations that converted the matrix into one that is in row echelon form. So the way we proceeded was to go column by column, where we determined if it was necessary to swap rows, and if so, we did. And then we added appropriate multiples of one row onto the rows below it to eliminate entries below that value. Recall that each row operation can be represented by a row operation matrix. So for example, for a 5-dimensional vector or a 5 by n matrix, we could swap either the second and fifth entries or the second and fifth rows by multiplying on the left by this particular matrix. Similarly, here we could add negative 0.7 times row 1 onto row 4. Recall also that we could find the inverses of these matrices. the row operations that undid the row operations we just performed. So for example, we could find the inverse of swapping rows 2 and 5, which is just swapping rows 2 and 5 again. So the inverse of the matrix on the left is itself. The inverse operation of adding negative 0.7 times row 1 onto row 4 is adding 0.7 times row 1 onto row 4. So the inverse of adding negative 0.7 times row 1 onto row 4 is adding 0.7 times row 1 onto row 4. Now you may not have thought of it, but if a matrix is in row echelon form, that matrix must also be an upper triangular matrix. Also, we applied a sequence of row operations to transform the matrix into one that is in row echelon form. Well, because each row operation can be represented by a matrix, then we could record these matrices and store them. So for example, suppose we have this 3 by 4 matrix, and we were to apply Gaussian elimination with partial pivoting. The first step we would take is to swap rows 1 and 3. Well, that's the same as multiplying on the left by the matrix that you see there. That matrix swaps rows 1 and 3. And the result now is on the right-hand side. Now, taking a look at that matrix on the right-hand side, to carry on the process of Gaussian elimination, we would add negative 0.4 times row 1 onto row 2 and add positive 0.3 times row 1 onto row 3. Well, both of these matrix operations can be represented, or row operations can be represented by matrices, and we would multiply on the left by them. Consequently, the first matrix you see there adds 0.3 times row 1 onto row 3, and the second matrix adds negative 0.4 times row 1 onto row 2. Applying those two matrices to the matrix that is on the balance, we get the matrix we see there, a matrix that has the largest entry in absolute value in the pivot location and all zeros below it. Now, given this particular matrix, we would continue on by first swapping rows 2 and 3, and then adding negative 0.9 times row 2 onto row 3. Again, both of these row operations can be represented by matrices. Consequently, we would now have that the application of these 5 row operation matrices onto the matrix A produces the matrix you see there that is in row echelon form. Thus, we have the following sequence of matrix multiplications. So we were converting A into a row equivalent matrix that is in row echelon form, and we had to apply 5 row operations. So starting from the right, we performed a row operation, then we added a multiple of one row onto another, then we added a multiple of the first row onto the third, then we performed another row swap, and then finally we finished with adding a multiple of row 2 onto row 3. Notice that these are not grouped according to the order. However, there is something interesting. It's possible to show that under certain circumstances we can swap these matrices. So for example, if we consider the second matrix from the left and the third matrix from the left, the second matrix from the left is a row swap operation. The third matrix from the left is adding a multiple of row 1 onto row 3. We can swap these two as long as we perform the same row operation onto the non-diagonal entries of the matrix. All right, we're not proving this. You can prove this is true yourself, but that's up to you. Similarly, we can swap the third and the fourth matrices now. Again, we had to swap rows 2 and 3, again on the off-diagonal entries. So this sequence of 5 row operations would have given us exactly the same result had we done them in that order as opposed to the order we found. Consequently, we have that A is row equivalent to the matrix on the right, where the first 2 row operations we applied are row swaps, and then the subsequent 3 are adding multiples of one row onto another. Now, suppose we know that the product of A times B is equal to C. Suppose we also know that A is invertible, in which case we can multiply both sides by the inverse of A. Easy enough. However, A inverse times A is equal to the identity matrix, and the identity matrix times B is just B. So what we've determined is that if A is invertible, then A times B equaling C is equivalent to B equaling A inverse times C. So, starting on the left, we can multiply both sides by the inverse of each of the square matrices. So we can start by multiplying by that row operation that adds 0.9 times row 2 onto row 3. We can now multiply both sides on the left by that matrix that subtracts 0.3 times row 1 onto row 2. We can then multiply both sides by the matrix that adds 0.4 times row 1 onto row 3. We can then multiply both sides by the matrix that swaps rows 2 and 3, which is the inverse of the matrix that swaps rows 2 and 3. And finally, we can multiply both sides by that matrix that swaps rows 1 and 2, which is again the inverse of the matrix that we see there. Consequently, we have that A is now equal to this product of matrices. If we now multiply all the row swap matrices together, we get a permutation matrix. Now, the next one is really cool because it only works because we add them in the order which they appear. But if we actually were to multiply those 3 matrices together, you actually don't have to do any matrix calculations. You will actually see that all that happens is that we copy the entries below the diagonal to their corresponding location in the matrix. So normally you'll remember that matrix multiplication is generally expensive. However, in this case and this case only, well, I guess there's other cases as well, but in this case, we don't actually have to do the tedious matrix calculation. You can do so if you want, but you will find that you get exactly what we see below, where we've simply accumulated all of the off-diagonal entries that were non-zero and placed them into their corresponding location. Finally, notice that the matrix that is left over is an upper triangular matrix. So now we have a permutation matrix, we have a lower triangular matrix in the middle that has all ones on the diagonal, and we have an upper triangular matrix. Okay, so now we know that A is equal to this product of three matrices with the properties we indicated before, and therefore we have shown that it is reasonable to suspect that we can always find a PLU decomposition for any matrix using the steps we just saw. All right, so now you may be thinking, so what? Yay, we can write any matrix A as a product of three matrices. Well, given a target vector V, suppose we want to solve A times U is equal to V for the vector U, which is unknown. Normally, we would, of course, create the augmented matrix. We would then apply Gaussian elimination with partial pivoting to find a row equivalent matrix in row echelon form. And then we would use backward substitution to find the vector U. Problem. We haven't discussed this in this class that much, but the Gaussian elimination step is computationally very expensive, much more expensive than backward substitution. In fact, if A is an n by n matrix and there is a unique solution, the Gaussian elimination step would take n times longer, approximately on average, to complete than the backward substitution step. So if you had a 1000 by 1000 matrix and the Gaussian elimination component took 1 second, then the backward substitution step would only take a millisecond. So it would be nice if we didn't have to perform Gaussian elimination as often as we did. All right, suppose instead of solving A times U is equal to the target vector V, suppose instead we are now solving a product of three matrices times U is equal to the target vector V. The vector U is unknown. We assume that we know all three matrices P, L, and the upper triangular matrix U. Step 1. Multiply both sides by the inverse of the permutation matrix P. Well, from the last topic, we saw that the inverse of a permutation matrix is its transpose. Thus, we have this expression here, and P transpose times P is equal to the identity. The identity times anything is what it is being multiplied by. So we are left with this expression here. So the matrix L times the matrix U times our unknown vector is equal to a permutation of the target vector V. Now, permuting the entries of a vector can be done very quickly. So there are very efficient data structures for storing permutation matrices, and there are very efficient means of carrying this out. Okay, so next step. We have two matrices times an unknown vector. Well, let's replace the matrix U times the unknown vector, and let's call it that a different unknown vector. Why? I don't know what the vector U is, so I don't know what the matrix U times that unknown vector is. So they're both unknowns. Let's just represent it by the unknown vector Y. Okay, now we have a lower triangular matrix times an unknown vector is equal to a permutation of a target vector. But if L is a lower triangular matrix, then we can just solve for the unknown vector Y by using forward substitution. That's fast. That's reasonably efficient. Okay, so we found Y. Having found Y, we can now solve for the upper triangular matrix times the unknown vector equaling the target vector. Well, that's easy enough too, because U is already an upper triangular matrix and is therefore in row echelon form. Okay, that's how we're going to use a PLU decomposition. Now, for example, suppose that a matrix A is a 100 by 100 matrix that describes the response of a graphene surface to various forces. You would like to simulate your design to see how your design responds to various different forces. You would therefore have a number of inputs. Let's say we have 200 inputs V1 through V200. And consequently, solving A times an unknown vector U sub k for each of the input vectors V sub k allows us to find the corresponding state of the system once those forces have been applied. This allows you to test your design before you actually go into the laboratory and produce your graphene surface, assuming, of course, that your design and your model is correct. Now, there are two possibilities that we could do here. We could use Gaussian elimination and backward substitution with every single input V sub k. We would then do that for all 200 and see how the system responds. Alternatively, we could once and only once calculate A as equaling P times L times U, and then for each of the 200 inputs, we would first use forward substitution to solve L times P transpose times our input vector V sub k, and we would solve that for an unknown vector Y sub k, and then we would solve the upper triangular matrix equaling this target vector using backward substitution. And again, the upper triangular matrix is in row echelon form. So now we are simply for every single target vector applying forward substitution and then backward substitution. With 200 simulations for a 100 by 100 matrix, the first would take approximately 40 times longer. This is going to be a serious impact on your employer's financial bottom line, and as an engineer, you have a responsibility not only to come up with safe designs, but also to safeguard the finances of your employer. For example, suppose we have this matrix A here, and here is its PLU decomposition. You can multiply out those three matrices and you will see that yes, indeed, the product of those three matrices does equal that matrix A. Now, with smaller matrices, it's harder to see the benefit, but you'll probably remember that the process of Gaussian elimination and backward substitution is itself somewhat tedious. So let's give it a go. Let's solve A times an unknown vector U for the target vector -8, 7.5, and 10, and then we'll do it again for the target vector 23.6, -0.1, -2. All right, starting with the first one, we multiply on the left by the transpose of the permutation matrix, which we have there. And looking at the first row of the permutation matrix, that says that we pick for the first entry the third entry of the original vector, 10. The second entry becomes the first entry, which was -8, and the third entry becomes the second entry of the original vector, which is 7.5. So now we substitute that into the lower triangular matrix, and that being the target vector. we can use forward substitution here. And looking at this, we observe that y1 must be 10, y2 must be -5, and y3, if we subtract off 4 and then add 5 times 0.9, we get 8. All right, so now we take the upper triangular matrix and use y as the target vector. Well, now we can simply use backward substitution since u is already in row echelon and therefore upper triangular form. So therefore, u3 is equal to -2, u2 is 3, and u1 becomes 1. So reasonably straightforward to solve. With the second example, again, we just multiply on the left by the transpose of the permutation matrix, which just rearranges the entries as appropriate. That becomes the target vector now for the lower triangular matrix. Solving this gives us that y1 is equal to, -2. It's easy when the diagonal entries are 1, isn't it? And the second entry, y2, is 23.6 minus 0.6, which is 23. Substituting -2 and 23 into the third equation gives us a y3 is equal to -20. All right, now this becomes the target vector for the upper triangular matrix. Looking at the last equation using backward substitution, u3 is equal to 5. Next, substituting 5 into the second equation gives us that u2 must therefore be equal to -4. And substituting both of those into the first equation gives us that u1 is equal to 0. All right. So in both of these cases, we rather efficiently and quickly found the solutions for these two target vectors. We did not have to do Gaussian elimination, and so therefore no row swaps and no adding of a multiple of one row onto another. Instead, we simply permuted the entries, performed forward substitution, and then backward substitution. All right, we will now describe an algorithm that finds P transpose L and U. We're going to find P transpose because that's what we're actually going to use to solve a system of linear equations. First, given an M by N matrix A, we will begin with 3 candidate matrices. P transpose will be initially the identity matrix. It will be M by M. L prime will be defined as L minus the identity matrix, and L prime will be initialized with the square M by M 0 matrix. The initial candidate for the upper triangular matrix will be the matrix A. Next, we apply the steps of Gaussian elimination as we learned them with just a few modifications. Each time you swap 2 rows, you swap 2 rows in all 3 matrices, P transpose, L prime, and U. Each time you add a multiple alpha of row I onto row J in the matrix U to convert it into row echelon form, we set the entry Ji of the matrix L prime to negative alpha. Finally, when U is in row echelon form, we are done. We have found U and P transpose, and we assign L the matrix L prime plus the identity matrix. Now, 2 points on this algorithm. If you understand Gaussian elimination, then you know how to find these three matrices. However, what's interesting here is that this describes an algorithm. You may wonder whether or not this algorithm actually does find the matrix decomposition. For example, you may be wondering why in this algorithm do we define L prime as being a zero matrix and then only swap the entries of the modified L prime matrix while not swapping the diagonal entries. Well, again, this is an algorithm. If someone gives you an algorithm, you should make sure that it works. For example, on one exam, students found an example of an algorithm that claimed to have solved the problem that they were asked to solve on the examination. However, the algorithm they found not only did not solve the question we asked, it also had an error in it. So again, always be careful to check your algorithms. To demonstrate this algorithm, we will apply it to the following 4x5 matrix. We could use a square matrix, but I'm just demonstrating that it works not only for square matrices, but also for non-square rectangular matrices. All right, so we start with our three candidate matrices. P transpose is the identity matrix. L prime, which is L minus the identity, is the zero matrix. And U is initialized with the matrix A. All right, we now proceed with Gaussian elimination with partial pivoting. So, looking at the first column of U, we note that we must swap row 1 and row 4. We do this in all three matrices. So now we proceed to add appropriate multiples of 4, or row 1, onto rows 2, 3, and 4. So we begin by adding 0.1 times row 1 onto row 2, and we store negative 0.1 in entry 2, 1 of the matrix L prime. Next, we add 0.4 times row 1 onto row 3. So once again, we perform that operation, but we store negative 0.4 at entry 3, 1 of the matrix L prime. Next, we will add negative 0.8 times row 1 onto row 4, and we store 0.8 in the corresponding location in the matrix L prime. All right, now we move to column 2. We note that we must swap row 2 and row 3. We do this in all three matrices. Now we proceed to add appropriate multiples of row 2 onto rows 3 and 4. So first we add negative 0.9 times row 2 onto row 3, and we store 0.9 in the matrix L prime. Next, we add 0.7 times row 2 onto row 4, and again we store negative 0.7 in the matrix L prime. Moving on to column 3, we have to swap row 3 and row 4. We do this in all three matrices. We must now add an appropriate multiple of row 3 onto row 4, which is negative 0.3 times row 3 onto row 4, and we store positive 0.3 at the entry 4, 3 of the matrix L prime. All right, so here we see now that the matrix U is in row echelon form, and therefore we are now finished. We now add the identity matrix onto the matrix L prime to get the matrix L, the lower triangular matrix, and we take the transpose of the matrix P transpose to get the matrix P. All right, so here are our P, L, and U, and therefore we have that the matrix A must equal this permutation matrix times this lower triangular matrix with entries 1 on the diagonal times this upper triangular matrix that happens to be in row echelon form. So following this topic, you now have seen a demonstration of how we can use the matrix row operations and matrix-matrix multiplication to suggest that a PLU decomposition is possible. You understand how to use this decomposition to solve a system of linear equations. You now are aware that this can be used to speed up having to solve a system of linear equations when there are many different target vectors while the matrix itself remains unchanged. And finally, you understand the algorithm for actually finding the matrices P transpose, L, and U. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!